Okay. So, today we will finally we will see the Dedekind's and Cantor's theory basically are equivalent concepts, both will give the same thing. Before going for this equivalence of Dedekind and Cantor's theory, we will see few more concepts or the things which can be represented with the help of the Cantor's theory, like the between any two real numbers there are infinite number of real numbers and so on and so forth. So, last time we were discussing about the index, is it not? And then in this case we have already seen that if n be a positive integer, if alpha is a positive integer, and x is any real number, x any real number, then x is any real number represented by the convergence sequence x n. Convergence sequence x n of rationals, of course, of rational convergence sequence rational, then x to the power alpha will be represented by the sequence x n to the power alpha, which is also a convergent one. This we see in case of positive integer. If it is negative, then we can just divide 1 by x n alpha. If alpha is negative integer, alpha is a negative integer, then we can write x to the power minus say m. This we can write as 1 by x to the power m, where m is positive. So, positive integer. And also we have seen if alpha is a fractional, alpha is fractional p by q, where p and q are the rational fractional, and in that case the x to the power alpha, that is p by q, this is the same as qth root of x to the power p, where x is taken to be positive, or it is defined when q is odd, and if q is odd, then even this can be defined for x is less than 0, can be defined even for x is if q is odd, q is an odd number. Okay. And the third case which we are discussing was if alpha is an irrational number, let alpha be an irrational number. We claim that x to the power alpha will be represented by a sequence x n to the power alpha, where x, where the sequence x n of rational numbers represents the real number x greater than 0. In fact, this is given when x is greater. So, I will just revise it, but we have already discussed this part. When alpha is positive integer and x be any real number which is represented by a convergence sequence x n of the rational, then index, we are talking about the index, the x to the power alpha will be represented by x n to the power alpha. And if alpha is negative, then we can write say alpha is equal to minus m, then we can write is 1 by x m, where m is say alpha is equal to minus m, then in that case x to the power minus m is 1 upon x to the power m, just m is integer. And if alpha is a fraction, then rational number, fractional, then x to the power alpha is nothing x to the power p by q, where this is nothing x to the power p and qth root of this when x is positive. But if x is negative, it can be defined provided the q is an odd number. So, this for integer and for fractional we have already discussed. Now, let us come to the irrational number. So, if alpha be an irrational number and let us suppose x be a sequence, x be any real number represented by a sequence x n of rational number, positive x is positive real number, then we claim that x to the power alpha will also be represented by x n to the power alpha. Okay, that we want our claim. So, let us see the proof of this. Okay. So, proof, let us see. Now, since sequence since alpha is a irrational number, alpha is a irrational number. So, it can be represented, by the sequence alpha n of rational numbers by Cantor's theory, is it not? Any sequence, convergent sequence of rational number represents either a rational number or irrational number and vice versa. So, if alpha is a rational number, we can identify a sequence alpha n, which convergent sequence of alpha n which represents the alpha. So, it can be represented by sequence alpha n of rational numbers, convergent sequence alpha n of rational number, that is important. Okay. Now, alpha n is a convergent sequence. So, it is bounded, alpha n converges, so it is bounded. So, since alpha n is a convergent sequence, of rational, so it is bounded sequence. It means less than some positive number for all n. Therefore, x is fixed. So, we get x to the power alpha n. Let x greater than 0 be any real number, okay. X n be any sequence of real number, and so x to the power alpha n, mod of this is less than equal to a. This I sorry, this just I wanted to, okay. Alpha be a resistance, we claim x to will be represented by, this you please make the changes, okay, by x to the power alpha n, because we are choosing alpha n, is it not, for the sequence alpha n of rational number representing the number alpha, okay. Just change please. What we are doing is x is any positive number, alpha is irrational. So, corresponding to alpha we are getting a sequence alpha n, x is fixed, so x to the power alpha we claim that represented by a sequence x to the power alpha n, because x is not going to change, okay, represent. Now, here alpha n is a sequence of rational number, so it is bounded. Therefore, x to the power alpha n will remain less than equal to a for all n. This is true for all n, okay, for all n. And a is for any fixed number, Now, sequence alpha n is a convergent sequence So, for a given epsilon, given small positive rational number epsilon, one can there exists some integer, there exists an integer so that such that mod of a alpha n minus alpha n plus r remains less than 1 by q for all n, for all values of r 1 to 3. Here I am taking epsilon to be 1 by q, epsilon to be 1 by q. Okay. So, for a given epsilon, say 1 by q I am taking such that this is less than epsilon. Is it okay? Now, q is any positive number. Okay. Now, consider mod of x alpha n minus x alpha n plus r. Consider this. So, take x to the power alpha n plus r outside. So, what inside we get x to the power alpha n minus alpha n plus r minus 1, is it not? Okay. Now, this may positive may negative. So, it is further less than equal to mod of x alpha n plus r into mod x mod alpha n minus alpha n plus r minus 1. Okay. Now, this x to the power alpha n, as we have seen from here, this is this one x to the power alpha n is bounded by a for all n. So, we can take this thing less than equal to a into mod x, and mod alpha n minus alpha n plus 1 is less than q, because this is convergent. So, it is less than 1 by q. So, it is 1 by q minus 1. Okay. Is it okay? And this is strictly, so we can say this is strictly less than this q. Okay. Now, this can be written as, I will write like this, is x to the power 1 by q into the, if I put it this way, a x minus 1 divide by okay. So, let x is greater than 1, let x is greater than 1, then we can write this modular sign x to the power 1 by q is greater than 1. So, modular sign is removed. Now, I am multiplying denominator and numerator by this number x to the power 1 by q, 1 plus x to the power 1 by q plus x to the power 2 by q up to x to the power q minus by q. So, when you multiply this, we are getting basically this sign x to the power 1 by q minus 1. When you multiply this by 1 plus x to the power 1 by q plus x to the power 2 by q and so on plus x to the power q minus 1 by q, then this is the expansion of 1 minus x minus 1, x is greater than 1. Okay. Because it can be written x to the, because this is equivalent to x to the power 1 by q, q minus 1. So, x to the power n minus 1, you just apply the binomial expansion, you will get this thing. So, what I did it, I multiply the numerator and denominator by this term, x is chooses to be greater than 1. So, this sign modulus is removed, then no problem, and we get x minus 1 over this. Now, since x is greater than 1, so each of this term in the denominator is greater than 1. X to the power 1 by q is greater than 1, x to the power 2 by q is also greater than 1. So, total values is q. So, basically this less than, this is less than a x minus 1 by q. Is it okay? Now, if I choose epsilon, we want this whole thing to be less than epsilon, is it not? To show this is a convergent sequence, we wanted this to be less than epsilon. So, if I choose q greater than a x minus 1 by epsilon, then what happened? This entire thing less than, then this entire thing mod of x alpha n minus x alpha n plus r, this remains less than epsilon r for all r 1 to 3 and so on. Because you just see, when you put it less than epsilon r, the q is greater than this number. Okay. So, this one we wanted this to be there. So, what this shows? This shows that if x to the power alpha n is a sequence of real numbers, okay, this sequence, then it satisfies the condition of the convergence, because the difference between any two arbitrary term of the sequence remains less than epsilon. So, x to the power alpha n minus x to the power alpha n plus 1 is less than this. Now, this shows, this implies the sequence x to the power alpha n is a convergent sequence. Okay. B represent this thing, we represent it by x to the power alpha, okay, x to the power alpha for x greater than 1 and alpha is a irrational point. Is it okay? Now, if x is lying between 0 and 1, then x to the power alpha, x n to the power alpha, this can be written as, or x to the power alpha n, which is equivalent to x to the power, is it not? This can be written as 1 by x to the power alpha n. If x lying between 0 and 1, then 1 by x greater than 1, is it not? So, if we consider this sequence, then can be written as this, x to the power alpha is this for x lying between. Now, consider 1 by x to the power alpha n. Okay. This is nothing but sequence 1 by x to the power alpha n, where 1 by x is greater than 1. So, as by the previous year, so by previous discussion this implies the sequence 1 by x to the power alpha n is a convergent sequence. Now, if x is 1, then x to the power alpha n, this sequence is equivalent to 1 only. Okay. Therefore, x to the power alpha n, this sequence represents the number, real number x to the power alpha for all x greater than 0, okay, for all x greater, and this will be an irrational number. Okay. So, that is what, is it okay? So, this represents. So, index can also be justified with the help of Cauchy sequence. Now, there are certain properties. In fact, these properties are parallel to our property which we have proved in case of Dedekind's. The property says is between any two real numbers, there lie an infinite there lie an infinite number of rational rationals. Okay. Between any two real numbers there are infinite rational numbers lie. Okay. Proof is just, let us suppose two real numbers. Let a and b are any two a and b be any two real numbers represented by the sequence say an and bn by represented by convergence sequences by convergent sequences an and bn respectively. Okay. And suppose a is greater than b, a is greater than b. Okay. So, now what we have? We have a sequence a which is represented by convergent sequence n. This means sequence n is convergent, sequence bn is also convergent, represent b, and a is greater than b. So, now apply the criteria. So, for a given epsilon greater than 0, for given small positive rational number epsilon, okay, we can find an integer, n such that mod of a n minus a n plus p is less than epsilon, mod of b n minus b n plus p is less than epsilon, and for p is equal to 1 to 3 and mod of a n plus p and a n plus, because a is greater than 1. So, a n plus p minus b n plus p. This difference is greater than or equal to some positive number delta, where delta is a fixed positive rational number. Fixed positive rational number. Okay. Now, this is because a n's are convergent, this is because b n is convergent, this because a is greater than b. So, a is greater than b means for any arbitrary terms, if you picked up from a and b, the difference must be positive. So, there exists some delta, some fixed positive such that all the terms of these differences will remain greater than or equal to delta. Now, let us, because epsilon is very arbitrary small number. So, I can choose the epsilon less than delta. Okay. So, let epsilon is less than delta, which is possible. Okay. That is not a problem. Okay. Now, let us pick up the rational number x, let x and pick up a rational number x lying between epsilon and delta, that is epsilon, this is greater than 0, less than x, less than delta. Let epsilon be x be a rational number lying between epsilon and delta. Okay. Now, consider a sequence, a convergent sequence a n minus x, in which all the terms are all the terms are identical with a n minus x. A n is a rational number, x I am choosing to be also a rational number. So, a n minus x is a rational number. Now, we can identify a sequence or we can construct a sequence where each term is a n minus x. Suppose I take 1, 1 is a rational number. I can construct a sequence 1, 1, 1, 1, 1, that is possible. So, corresponding to rational number we can identify this. So, let us take a n minus x as a sequence whose each term is identically equal to a n minus x. Okay. Now, this will be okay. Now, consider a n plus p minus a n minus x. Now, from here if you look, a n is convergent. So, this condition is satisfied, a n minus a n plus p is less than epsilon. It means a n plus p lies between a n minus epsilon and a n plus epsilon. So, from here we can say, since mod of a n minus a n plus p is less than epsilon for p equal to 1 to 3. So, basically a n plus p lies between a n minus epsilon, a n plus epsilon, is it not? So, if I want this number, say this one, then we can say a n plus p is greater than a n minus epsilon minus of a n minus x. Just substitute here, is it not? So, from here we get this is greater than x minus epsilon, but x lying between 0 and delta, which is greater than epsilon. So, this is basically a positive. So, this implies that the number a sequence a and p is a convergent sequence which represent the number a. So, this implies the real number a represented by a convergent sequence a n plus p or a n, what is okay, same, is greater than the real number a n minus x, because this is a real number which I am choosing a rational mean real, okay, is number greater than this. On the other hand, consider the difference a n minus x minus b n plus p. Now, this we can write it as a n minus b n plus b n minus b n plus p minus x. Now, a n minus b n and b n plus p. So, what is this a n? This a n plus p minus a n plus p is greater than equal to delta. So, this will be basically greater than delta after a certain stage. This is for after certain stage, this is greater than delta. This will be b n minus b n plus 1 lies between minus epsilon and plus epsilon. So, I can say b n plus a is greater than minus epsilon, that is greater than minus epsilon, and then minus x, and then this is minus x. Okay. For after some integer, after certain integer n, after an integer n, suitable integer n can be obtained. Okay. Now, this can be made greater than 0, which is greater than 0 if we choose, if x is chosen to be less than delta minus epsilon. If I choose x to be less than delta minus epsilon, because what is there? this delta here epsilon. So, delta minus epsilon is positive quantity, So, if I take an x, any number which is less than delta minus epsilon, so for that particular x, this term will be greater than 0. Now, this represents the real number a n minus x, this represents the real number b. So, what is the real number a n minus x is greater than b. So, this implies that the real number a n minus x is greater than b. So, now what we conclude is that a n minus x, this is a real number which is greater than b, but less than a, is it not? This is a real number which lying between b and a is greater than b, but x is our choice, because one can choose infinite x which satisfy this condition. Between epsilon and delta, we can take infinite number of x which can satisfy this condition. So, as soon as you change x, there are infinite number of real point lying between a and b, and in fact, these are all rational points. These are all rational point, because a n are rational, x is also rational. So, and we are taking a sequence corresponding to n minus x itself. So, it is a rational number. So, this implies, but x can be chosen arbitrary in between epsilon and delta, such that delta minus epsilon is greater than x. Okay. Therefore, there are infinitely many rational lying in between a and b. That is proved. Okay. So, clear. The second property is that in between any two real numbers, between any two real numbers, there lie an infinite number of irrational numbers. Okay. So, there lie infinite number of, proof is very simple. Just suppose a and b are the two real numbers, where a is greater than say b. Let us assume v is rational, b is rational. Okay. Okay. Now, if alpha be a irrational number, if alpha be any irrational number, in rational numbers, then we can find a positive integer n such that alpha by n is strictly less than a minus b. What happens is, this is our number b, here is number a. Now, you picked up any alpha, any irrational number alpha. So, n can be made as large, and we can choose as large as possible, so that alpha by n lies between here. Alpha by n lies between this. It means, this implies that the number b plus alpha by n, this number is irrational number, is it not? Because alpha is irrational, n is integer of course, and lying between b and a, because it is greater than a, b plus alpha n is greater than b, but is less than a because of this relation. So, this number is a irrational number lying between b and a. It means between any two real number we can find out a irrational number. Now, if b is a irrational, because we have assumed one is to be rational, if b is irrational, then we can find a rational number beta we can find a rational number beta which is less than a minus b by, this is our b, this is a. So, if b is a irrational number, then we can find a rational number between b and a, because a and b are the two real numbers, these are real, this is real. Between any two real number, there are infinite many of irrational points. So, between a and b, one can introduce a irrational number, one can identify irrational number beta, because between any two real, there are infinitely many irrational points are there. So, there exists, we can find a beta which is less than a minus b.
Beta is rational.
Rational, beta is rational, which is lying between this. So, this implies that b plus beta, b is what? B is irrational. So, b plus beta is an irrational number, and b plus beta is greater than b, but less than a, is it not? Because it is less than a minus b. So, b plus beta is less than a. So, in between two reals, this is real, they are real, we can identify a irrational point again. So, therefore, this proves the result. Okay? This proves the whole thing. That would be. Is it okay? Now, before going for the limit etc., we will see the main things, that is the equivalence definition of Dedekind's and Cantor's. Okay. So, let us see equivalence of the definitions of Dedekind and Cantor. This was the main. Means we have developed the concept of the real numbers with the help of Dedekind cut as well as the concept of the convergence sequence of rational points, and this is given by Cantor's and the cuts given by the Dedekind. And what we see that these two theory basically are equivalent, they give the same set of the real numbers, do not give it. Okay. So, what is the difference between them? If we take the Dedekind's theory, Dedekind's cut, here what we do is here quite the B in Dedekind's cuts, in Dedekind's theory we consider the entire set of real number, consider the entire set of rational numbers and on this set of rational numbers we are introducing the cut, is it not? Then we say a lower class and upper class, and that things, any rational number which belongs to either lower class or upper class, and like this. So, in Dedekind theory or Dedekind cuts, we consider the entire set of rational number together at a time. Okay. While in Cantor's theory, the sequences we consider the sequences of rational numbers, out of this set, out of the earlier set, is it not? This set of rational points, we picked up the sequence of the rational number and then we said this converges to a real, converges to a rational, converges to irrational point. So, this in Dedekind's case we consider at a time all the rational points and put it in the form of the sections cuts, while in case of this we bring the sequence of the rational numbers and then we assign the limits to this sequence, converging sequence of rational numbers, sometimes rational and irrational. So, this is the main idea which they have done. However, fundamentally they are true. However, they are equivalent. They are equivalent to each other. They are equivalent to each other. That is, for a section of all rational number, that is, for a section of all rational numbers, for a section of all rational numbers can be defined corresponding to an any convergence sequence of rational number. Rational numbers, and conversely a convergent sequence of rational number can be formed. Conversely, a convergent sequence of rational number can be formed from any given section of rational number, given section of rational numbers. Okay. This is the, so we can introduce that, we can define. Now, let us see the proof of this, how these two theories are equivalent. So, we need the following theorems. First result is to justify it, we have the following results. Okay. The first result is the section corresponding to a convergence sequence. To a convergent sequence. Okay. Let us see. So, let x n be a convergent sequence of rational numbers. of rational numbers let x n be a convergent sequence of rational number which defines the real number x. Real number x, and let a be any rational number, and let a be any rational number, a be any rational number represented by a sequence A, where all the terms are the same a, and consider x minus a. Now, consider the real number x minus a represented by a convergent sequence x n minus a. Let us see this. Okay. So, what we have this concept. Suppose we have this x here and a is any rational number here. Okay. The x n, if a convergent sequence of rational number defines the number x. So, x 1, x 2, x n can be obtained here. This is x 1, x 2 and so on, or it may come from here also x 1, x 2, x n. A is a number which is the a itself. So, we do not care for it, we do not bother about much. Then x n minus a, this is very important thing, represented by x minus a. Now, let us see. Now, if this number, if x minus a is different from 0, Now, since x minus a is represented by x n minus a, which is different from 0. So, either it means what? That after a certain stage, all the terms of the sequence will have one sign, either it will have a positive or it will have a negative. Any number, if x minus a is different from 0, because this we have seen, if x minus a is different from 0 number, then either it will be positive number or it will be a negative number, is it not? So, the corresponding sequence x n minus a will have only one sign, either it will a positive or it will be negative after a certain stage n onward. Okay.
It is convergent sequence.
Obviously, because x n minus a is represented represents the number x minus, which is a convergent. This is a convergent sequence. Okay. So, is not then from n after some fixed, from n after some fixed values of n, x n minus a has a fixed sign, is it not? So, this is clear, because of this has fixed sign, that is either positive or negative. This sign will be there, either positive or negative, according to the value of a. Depends on a, whether according to a. If a is greater than this or negative, otherwise it will be positive also. So, okay. Let us suppose, let every number a, which is such that x n minus a is positive for n greater than or equal to say n naught. After a certain stage, it greater than n naught. Now, let us define classes. As follows. What we take L is the class of those number a, for which a n minus or x n minus a is positive after certain integer n naught. Let us put it in the class L, okay, after a certain integer, and R we are every number A for which is negative, and those numbers A for which x n minus A is negative, x n minus A negative after certain integer n, after certain integer n, let it be placed in the class R. Okay. So, those numbers which are greater than 0 is in the class lower class, which are less than 0 in the upper class, yes, upper class of certain integer of this negative from and after certain integer. If there exists a for which neither of the, okay, and third case is, so let us see. So, this is our what we have given the x equal to this sequence convergent. So, I am taking x 1 x 2 x n like this. I am putting those rational number, those number A in the lower class such that after a certain stage the difference between x n minus A is positive. So, these points will come, is it not? So, those real numbers for which this is greater than 0 will be put in the lower class, while the upper class means A is this. Suppose I take this number like this. So, A is this number, x n, x 1, x 2, x n will be this. So, x n minus A will be negative after a certain stage. So, those number you are putting to be in the upper class. Now, obviously, this forms a section A. This section clearly, okay. In third case, what about the A? Third case is, now if there exists a rational number A, if there exists a rational number A for which neither of these cases arise, neither of the above cases arise, neither of the above cases arise, then maybe neither of the above cases arise, then x is equal to A, and may be put up in either of the class. Okay. Now, we claim this way the section X, this will give the corresponding section corresponding to the number X. Okay. Now, this is we claim this will give a section corresponding to X. So, we will see next time the detail for this. Okay. But it is almost completed, just a few minutes. Okay, thank you. In fact,